Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. So in this problem, we have two current carrying wires carrying currents in the opposite direction, and they're being suspended by ropes. Now, because they're carrying currents in the opposite direction, right, each of those wires creates their own magnetic field, and then the magnetic field from one wire interacts with the current in the other wire, and these result in magnetic forces. And we know that if wires carry currents in opposite directions, they're going to cause repulsive forces. So overall, we have a situation that looks something like this, right? So we have wires being suspended from the ceiling by ropes. And because the distance between the wires is going to be important, I'm going to draw this line right here, and then I'm going to draw our wires being suspended from these ropes. Let's call the wire on the left wire 1, and we'll have that current going into the page here, represented by an X, and the current will have a magnitude I. This wire here will be wire 2. It'll be carrying the current out of the screen. We know from the problem that the current is the same value, so the same magnitude of current in each, but of course they're in the opposite direction. So we have the dot here representing the current going out here. Okay, we also know the lengths of these wires here, L, and we also know the entire angle here, and we'll call that angle theta, right? And we know that is going to be 15 degrees. We also know this length, little l here, is 1.2 meters. Now it's going to be nice and useful to bisect this angle, right, so that we know that these make two right triangles, each with half of theta as an angle. There we go. Two right triangles here. Okay, another important factor or variable we're going to need for this problem is the distance between the two wires, and we know that that's represented as this line I've drawn here, the bottom of this triangle, and so it's going to be a distance of r. Let me better represent that. So this entire distance between the two wires is r here. Okay, good to know. And we can also see, since we're getting to know this length here, we can tell what that's going to be by looking at the equation, or just doing some trigonometry here for these two triangles I've just drawn. So if I want to know how long this length of this triangle is here, since this is a right triangle and the angle opposite to it is 1/2 of theta, then I know the length of half of this r here is going to be L times sine of the theta we're given over 2. So really it's sine of 7.5 degrees, which is half of 15. Anyway, we've done a little bit of geometry to set up this problem. Now really what we're going to need to know in order to figure out the currents of these wires is the forces acting on these wires. Because what's happening, right, is that not only is gravity trying to weigh these wires down because they are massive wires, the magnetic force between the two wires are repelling each other. So now what we're going to do is think about what are the forces acting on our wires and then in what directions. So why don't we just do a little bit of thinking here. So let's just focus on wire 2. Because they carry the same current, we can figure out the current in each just by solving for the current in one. So let's go ahead and work on that. So for our wire 2, we know that's going to be experiencing a gravitational force straight down. We'll call it F sub g, and that's going to be of magnitude m times g. The mass of this wire multiplied by the acceleration due to gravity. Now, we also know that the wire is going to feel a repulsive magnetic force from the other wire directly to the right here. And we'll call that the magnetic force of wire 1 on wire 2. Now, what is that going to be given by? Right, well, it's going to be given by the current going through wire 1 times the length of wire 1 multiplied by the magnetic field created by, sorry, let me say that again. This is the force of wire 1 acting on wire 2. So it's going to be given by the current going through wire 1, the length of wire 1, and sorry, let me say that again. This is the force of wire 1 on wire 2. So this is actually going to be the current flowing through wire 2 multiplied by the length of wire 2 multiplied by the current through the magnetic field created by wire 1. Now, we also need to multiply this by sine of the angle between the magnetic field created by wire 1 and the current direction in wire 2. The magnetic field created by wire 1, given our right-hand rule, if we put our thumb into the screen along the direction of the current, then our magnetic fields, like our fingers, are going to curl around in a clockwise, rewrite that, in a clockwise manner. That means at the location of wire 2, the magnetic field, due to wire 1, is actually going to be headed straight down. And is going to have a magnitude of mu naught times the current through wire 1 divided by 2 pi times r, which is the distance between wire 1 and wire 2. Okay, good to know. Now, if the magnetic field created by wire 1 is headed straight down, and the current in wire 2 is headed straight out, then those two things are perpendicular. If those two vectors are perpendicular, phi is then 90 degrees, and sine of phi goes to 1. So that we know that the magnitude of the magnetic force acting on wire 2 caused by the magnetic field created by the current in wire 1 is given by, in magnitude, by the current through wire 2, the length of wire 2, and the magnetic field caused by wire 1. And we know what that is. So we can plug that. We know that that is. It's right here. So we can plug that in. So we have that the force acting on wire 2 from wire 1 is given as IL times mu naught times I all over 2 pi times how far apart the wires are from each other. Now when I simplify this out, I'm just going to group a few terms here. I'm going to see that the magnetic force acting on wire 2 from wire 1 by magnitude is mu naught divided by 2 pi multiplied by the length of wire 2, which they're both the same length, so the length of our wires, divided by how far apart our wires are, multiplied by the currents squared. So the current in each multiplied together, but they have the same currents, so it's the current squared. So we have the magnetic force, the gravitational force acting on wire 2, the magnetic force acting on wire 2, and what else is acting on wire 2? Well, of course, remember, we have a tension heading up into the left. So that's going to be, we'll label it as F sub t for the tension, and that's going to be heading up in that direction, like so. Okay, so now what we want to do, now that we've figured out what the forces are acting on our wire, we want to rewrite this as a free body diagram. So what I'm going to do is use this room at the bottom to draw a free body diagram for our wire 2. And then we can figure out Newton's dynamics based on what's happening in this problem, and then from there, through Newton's laws, we can figure out the current through the wires. Now, let's draw a free body diagram. So let's represent our wire 2 as just a dot. We know that the force of gravity heads straight down of magnitude m times g. We know that the magnetic force heads straight to the right of magnitude mu naught over 2 pi L over R I squared, and we know that we're going to have a current heading up and to the left at the same angle of 1/2 of theta, because that is the same alternate interior angles that we have in our diagram here. And this is going to be the magnitude of the tension force. So now we know all the forces acting on our wire, and we know that this wire is suspended at rest. so that we know that the total acceleration of the system of this wire, A with a vector, is 0. So that means that for this wire, that the net force, so the sum of all the forces acting on our wire, is equal to 0 in both directions. So that means if we sum up all of the forces in the x direction, that would be equal to the mass times the acceleration in the x direction, but that is 0 because ax is 0, because the total acceleration is 0. And the sum of all the y forces would tell us the same thing about the y acceleration, but again, it's also 0 because overall this wire is not accelerating. So what do? We take we set up a coordinate system, we break our forces down into components, and then solve these two equations for Newton's second law. So what I'm going to do is going to clear out this, rewrite our free body diagram so we have something to reference, and then do all of our Newton's second law problems, do all our Newton's second law equations out. So let me real quick redraw our free body diagram. Gravitational force heads straight down. And right, we have our magnetic force of magnitude given by this equation. And I can just, for clarification, write out our variables for our forces. Okay, so now we just need to do some trigonometry to break down our tension force into two components. Now, our tension force goes along this diagonal here, and it's off at an angle of theta over 2, or 7.5 degrees. If we want the y component to our tension, we want the opposite side, so it's going to be sine. So we have the magnitude of the force of tension times sine of theta over 2. That's going to be our horizontal component of our tension force. And then we know that f of t cosine theta over 2 is going to give us our x component of our tension force. Now, we need to set up a coordinate system. I like to pick one. I like to line up a coordinate system that has as many of our forces aligned with it as possible. So I'm going to pick one like this. So I'm going to have a positive x going to the right and a positive y going up. So now let's remind ourselves that we're going to do Newton's second law analysis here, so that the net force is going to be equal to the mass of our system times the acceleration, but we know that that's going to be 0. So we're going to do this in each direction, right? So for our x direction, let's add up all the forces in the x direction and then set them equal to 0. So what do we have acting in the x direction? Well, we have all of our magnetic force of wire 1 on wire 2 acting in the positive x direction, and we have the x component, or of the tension force magnitude multiplied by sine of theta over 2, acting in the negative x direction. And those are all the forces and the components of those forces acting in the x direction. So we're done with the left-hand side of Newton's second law. Then we set it equal to, well, ma x, but that is 0. So we have our first x equations for Newton's second law. We do the same thing for y, so we sum up all the forces in the y direction and set that equal to, well, technically may, but that's going to be 0 in this case. So what are all the positive components of forces in the positive y direction? Well, I have my vertical y component of the tension, given as ft cosine theta over 2 in the positive direction, and I have all of my weight, mg, acting in the y direction. That's it for our left-hand side of Newton's second law. Set that equal to may, but we know that ay is 0. So now we have two equations to solve, and this is going to enable us to find out the currents, right? Because we know that the current is wrapped up in this expression here. So let's solve, because we do not know the value of the tension, let's solve for the tension in one of our equations, say the one we got for balancing the y forces, and plug it in to our equation in the x direction. So solving for the tension force magnitude using our y equation here, we see that it's just the weight of our wire divided by cosine of 1/2 of the angle given to us. Now we can take that and plug it into f of t in our x equation. Right? So let's rewrite our x equation. F sub 1, 2 is, by magnitude, mu naught over 2 pi L over R times I squared. And that's going to be equal, right, given this equation here, that is going to be equal to Ft sine of theta over 2. But let's plug in what we just found for Ft mg over cosine into here. So we have mg over cosine theta over 2 multiplied by sine of theta over 2. What does that give us in the end? That just gives us an mg, well, sine of theta over 2 divided by cosine of theta over 2 would be tangent of theta over 2. Just to simplify things out a little bit more. So now we see we have mg, or the weight of the wire, multiplied by tangent of half of the angle given, and that's going to be equal to this expression for the magnitude of our magnetic field strength. So why don't I put those two things equal to each other on the next screen and then solve for the current, because that's what we want to find. And remember, what we did is we looked at our situation, the dynamics of our situation, figured out the forces acting on our object, and then did a Newton's second law analysis to figure out the current. So let's rewrite that statement real quick. From balancing all of our forces, solving for the tension force we didn't know, and plugging it in to our other equation, we get that the magnitude of the magnetic force is equal to the weight times tangent of half of the angle that we were given. Solving for I here, what we see is we're going to have I is equal to, well, the square root of a bunch of stuff. So we have our mg tangent theta over 2. Right? This multiplied by, 2 pi r, and then divided by L and mu naught. Now, one thing we need to figure out from before is what this distance r is here. If we go back to our diagram and rewind the video a little bit, you'll see something that looked like this, right, where we had our two wires hanging at theta over 2 here. This whole distance here was r, and this little distance here was L sine of, maybe I have this better. So this whole distance here is r, and this little distance here is L sine of theta over 2. Now you'll see that the entire r then is 2 of these L sine theta over 2 values. Okay, so r is going to be equal to 2L sine theta over 2, and that gives us our last final expression to where we can now start plugging in things that we know. So we have the mass of our object, the mass of our wire divided by the length of our wire, and that actually will be an important quantity in a second, multiplied by the acceleration due to gravity, multiplied by tangent of our angle given divided by 2, and then multiplied by doing plugging this into here, 4 pi L sine of theta over 2. And this is all going to be divided by mu naught. Okay, this is a large, big expression. You'll notice that in the problem, they don't give you the mass of the object, they give you the mass per unit length. And so you'll see that this is what we're going to plug in for that, right? So we're going to plug in the 0.050 kilograms per meter into this variable here. And then everything else should be pretty self-explanatory to plug into. G is 9.81, the theta is 15, L is our 1.2 meters, and mu naught is our 4 pi times 10 to the negative 7 Tesla meters per amp. So I'll let you all plug that into your calculators, and in the end what you should get is an answer for the current flowing through both wires, and it's going to be 320 amps. And that's our answer.